This problem and all other Calc 152 problems can be found here at Sarai Studies. Link is in the description box below. In Calc 2, before you even read the problem, if you can spot the word volume, you already know you're going to do either one of two things: face or time. These are the two methods that I came up with for finding volume. Which one are you going to use? Well, if you keep reading and you spot the word revolving, that means you're going to use time. I like to think of it as the clock revolves around time. So when I see the word revolving, I'm going to use the time method. What's really the difference? Time is used to find volumes of regions that were revolved around an axis and they formed a solid. Face we use for problems where we try to find the volume of solids that are not revolved but are just simply made up of cross sections. So T stands for terms. This is to decide what terms our formula is going to be in. Is it going to be in terms of x? Is it going to be in terms of y? This depends on two things: the axis of rotation and the method that you're using. The axis of rotation is always given to you. It is the x-axis. In order for this to work, you have to always put your axis of rotation in equation form. So x-axis is really y is equal to 0, right? Opposite. So this is y is equal to 0. Now, as for the method, the big question always is, what method are we going to use? The misconception is that, oh, there's only one method to use in one problem. No. For most problems, washer and shell can be used and get the exact same answer. One may be harder than the other, but that's for you to find out. But before analyzing which one's harder, you can have an inkling of which method you would prefer. So my thought process is always to look at the equation that they give me and I look at the terms that that equation is in. In this case, because the terms are literally x, then my equation is in terms of x. And honestly, I like the way that it is right now and I don't want to rewrite it. So I want to choose a method that's going to allow me to keep the same terms. So here's where the rules come in. You have two rules. If you do disk or washer, they're the same method. Think D for different, take this letter, do the different one, the opposite, that's x. So in this case, if we do disk and washer, then everything's going to be in terms of x. I would have my equations in terms of x. I would have a dx integral. My bounds would be x is equal to something and x is equal to something. And that's exactly what I want because my function, or my equation in this case, is already in terms of x. The term is literally x, so that saves me work. If I were to do shell, which is the other half of the rule, S for same, take the same letter, that's y. Everything would have to be in terms of y, including my functions, in this case my equation. That means that I have to solve for x to get the terms y, and that's more work for me. So my thought process is, okay, let me choose the method that's going to give me less work, and that allows me to keep my equation already in the terms that it already is, and so that is disk or washer. So D for different, take the opposite letter x, everything has to be in terms of x. That means we're going to have a dx integral and our bounds are going to be x is equal to something and x is equal to something. Now, this isn't the end all be all. This is just the method that we can try first and we can see if it works. So how can we confirm that this is the method we want to use? By graphing and just visually saying if we have everything we need for the method. We're also going to keep an eye out for split integrals because then that changes things. Maybe we don't want to do a split integral, so maybe we'll want to try the other method. So we have to take those things into account. So to graph, you never have to graph the actual solid of revolution. Don't worry, it's just the graph. You could always use an x and y table. I always start with graphing the intercept, so that's 0, so it's going to be here, and I know it's going to look something like this. X is equal to 2 is over here, and this is y is equal to 0, and then this over here is the region bounded by these lines and curves. And we're revolving this region about the x-axis, but that's not really important right now. What's important is I want to make sure, I want to confirm that we can use this method. And if we can, then perfect. It works for us because everything's in terms of x and we don't have to check any other method. If not, then we can check if another method works. So what I do is if I have disk or washer as my options, I always do the formula for washer because if things are not found in washer, and you'll see what I'm talking about in a second, then it just automatically becomes disk. And if that doesn't make sense, just give me a second. So the way that I derive the formula for washer is think of a washing machine. A washing machine has a hole in the center where you can see clothes inside, or at least one type of washing machine. So the idea is that you want to find the area of this shape right here, but there's a hole in the middle. So ideally the area of the big shape is pi big R squared because it's really just a circle. It's a disk, it's a circle filled in, but it's really just a circle. The area of the circle is pi R squared. And the area of the smaller circle is pi with the smaller radius squared. And you can see it. Here the radius goes from here to here, and here the radius goes from here to here. Which one's bigger? This one. So it's bigger R. So the idea is that we want to take both of the areas and subtract them. So we're taking the area of the bigger circle and subtracting the area of the smaller circle so that we can get the area of this shape right here, of the big circle with the hole in the middle. And if we do the integral from a to b, that's volume, and notice we can take out a pi, so that becomes rx squared minus little rx squared. And then because it's a pi, the constant, we can bring out the pi to the front. And don't forget dx. So we have our graph in terms of x, and we also have a dx integral. Now let's actually confirm we can use this method by finding out if we have everything we need. I always start with the inner radius. The inner radius is just the distance from the axis of rotation to the first graph that I touch. That is this distance right here, from here to here. This distance, that is my radius. But right now I don't actually want to find it. I just want to know it's possible to find it so that I know that I'm in the right track of using this method. But then I go and see my bigger radius. My bigger radius is the distance from the axis of rotation, which is the x-axis, all the way to the second graph. But wait, I don't see a second graph. So what does that mean? The big hole doesn't exist. Therefore, I only have that purple hole and I don't have to subtract anything, and it just becomes disk. So that's why I tell you start with washer first, and if there's something missing, then it just automatically becomes disk. That's why disk and washer are basically the same thing, because disk is just the area of one. And so already I know what this is. So I know it's possible, and so therefore I confirm, okay, I can use this method. So in other words, I kind of do these problems in my head using the graph just to confirm that I can do them. And if I can't, then I go to another method, and you'll see that in another video. So we're going to be using disk. And so this is simply from the axis of rotation, the distance from here all the way until you touch your first graph. This little length right here, that's your radius. So it touches this graph, x cubed, y is equal to x cubed, and then here this is y is equal to 0. So it's really the difference between x cubed minus 0, which is why your radius is equal to simply x cubed. And remember, we're squaring that dx, and then we still need to figure out our bounds. What are bounds? That's what the I stands for. It's our interval or our bounds. I also stands for intersection. If you don't have a graph for some reason, the way that you find the bounds is by setting your functions equal to each other. But oh wait, it's kind of hard to look at this and be like, okay, what should I set equal to what? And that's why we graph. It makes things so much easier because look, I already know that my bounds have to be x equal to something and x equal to something. So I just look, my bounds is really the starting of my shaded region to the end. It's 0, and then they're literally giving it to me, it's 2. So that's why graph it, it's so much easier to tell things. So from 0 to 2, that is my interval. Look at how easy that was. So we have from 0 to 2 multiplied by pi. This is really x to the 6. And then we can do power rule, plus 1, that's a 7. So divide by that same thing. Pull out the 1 over 7, this is x to the 7th, then this is being evaluated from 0 to 2 multiplied by pi. Then fundamental theorem of calculus, oh wait, I'm getting ahead of myself here. E stands for evaluate, so we're supposed to be doing this over here. Evaluate the integral. Fundamental theorem of calculus states, take the 2, plug it in, and take the 0. So 2 to the 7th minus, well, this just becomes, this whole thing becomes 0. But I know 2 to the 4th is 16, and 2 to the 7th is 128, so that's going to be 128 divided by 7. That's being multiplied by pi, and so this becomes 128 pi over 7 cubic units because we're dealing with volume, and that is your answer.